The bond wire between the meter base and the service panel serves the critical purpose of establishing a low impedance path for fault current. Let's delve into the reasons why this is so important. When a fault occurs, such as a service wire coming into contact with the meter base enclosure, a large amount of current will flow. Without a proper bonding connection, this fault current would seek alternative, potentially hazardous paths back to the source, which is the transformer. These alternate paths might involve equipment grounding conductors, metallic conduits, or even building steel. The impedance of these paths can be significantly high compared to a dedicated bonding conductor. Higher impedance results in a greater voltage drop along the path, and in turn, a lower fault current. This lower current may not be sufficient to quickly trip a circuit breaker or blow a fuse, thus failing to clear the fault in a timely manner. A persistent fault current can lead to several problems. Firstly, it can cause overheating of conductors and equipment, potentially leading to fires. Secondly, it can create a shock hazard, as metallic parts of the electrical system could become energized with dangerous voltages. Thirdly, it can damage sensitive electronic equipment due to voltage fluctuations and electrical noise. The bond wire, typically a copper conductor sized according to the applicable electrical codes, provides a direct and low impedance path back to the service panel. From the service panel, the fault current can then flow back to the transformer via the neutral conductor, which is intentionally grounded at the service entrance. This low impedance path ensures that the fault current is high enough to quickly activate the overcurrent protective devices, such as circuit breakers or fuses, in the service panel. The rapid clearing of the fault minimizes the duration of the hazardous condition, reducing the risk of fire, electric shock, and equipment damage. Now, addressing the question regarding overcurrent protection and the secondary side of the service conductors. It is true that there isn't an overcurrent protection device specifically dedicated to protecting the service conductors between the transformer and the service panel. This is because the service conductors are considered to be very short and are installed with a high degree of physical protection. Moreover, the transformer itself has inherent impedance that limits the maximum fault current available on the secondary side. However, the primary function of the bonding system is not to protect the service conductors themselves, but rather to protect equipment, personnel, and the overall electrical system from the hazards associated with ground faults. Even though the service conductors might be able to withstand a short-duration fault current, the other components of the electrical system, such as the meter base, the service panel enclosure, and connected equipment, may not be able to. The bonding system ensures that these components are effectively grounded, so that fault currents are safely conducted back to the source and quickly interrupted by the overcurrent protective devices in the service panel. The National Electrical Code, or NEC, provides specific requirements for bonding and grounding electrical systems. These requirements are designed to ensure that the electrical system is installed in a safe and reliable manner. The NEC Article 250 covers grounding and bonding, and it provides detailed guidance on the proper methods for bonding various parts of the electrical system. For example, the NEC specifies the minimum size of the bonding conductor based on the size of the service entrance conductors. It also requires that the bonding conductor be securely connected to the meter base and the service panel using approved connectors. It is crucial to adhere to the NEC requirements when installing and maintaining electrical systems. Failure to comply with the NEC can result in serious safety hazards, as well as potential code violations and fines. In summary, the bonding of the meter enclosure to the service panel is essential for electrical safety. It provides a low impedance path for fault current, which helps to prevent damage to equipment, reduce the risk of electric shock, and minimize the likelihood of fire. While there may not be dedicated overcurrent protection on the secondary side of the service conductors, the bonding system works in conjunction with the overcurrent protective devices in the service panel to ensure that faults are quickly cleared and the electrical system is protected. Always consult with a qualified electrician and follow the applicable electrical codes when working with electrical systems. Here's a more detailed explanation of some key aspects. Firstly, impedance versus resistance. While both terms describe opposition to current flow, impedance is a more general term that includes resistance and reactance. Reactance is the opposition to current flow caused by inductance and capacitance. In alternating current, or AC, circuits, both resistance and reactance contribute to impedance. Secondly, fault current path. The fault current path consists of the following elements: the point of the fault, the grounding conductor or bonding jumper, the grounding electrode conductor, the grounding electrode, the earth, and the neutral conductor back to the source. Thirdly, touch potential and step potential. Touch potential is the voltage difference between an energized object and a grounded surface that a person could touch. Step potential is the voltage difference between 2 points on the ground that a person could step on. Proper bonding and grounding can help to minimize touch and step potentials, reducing the risk of electric shock. Fourthly, equipment grounding versus system grounding. Equipment grounding connects non-current carrying metal parts of equipment to ground. System grounding connects the neutral point of the electrical system to ground. Both equipment grounding and system grounding are important for electrical safety. Fifthly, surge protection. Bonding and grounding also play a role in surge protection. A properly grounded electrical system can help to divert surge currents away from sensitive electronic equipment, protecting it from damage. Sixthly, the importance of proper connections. Loose or corroded connections can increase the impedance of the grounding path, reducing its effectiveness. It is important to ensure that all grounding and bonding connections are clean, tight, and corrosion-free. Seventhly, regular inspections. Electrical systems should be inspected regularly to ensure that the grounding and bonding system is in good condition. Inspections should include checking the condition of grounding conductors, bonding jumpers, and connections. Eighthly, qualified personnel. Electrical work should only be performed by qualified electricians who are familiar with the applicable electrical codes and safety procedures. Now let's talk about specific NEC sections related to this topic. NEC section 250.4 discusses general requirements for grounding and bonding. NEC section 250.24 covers grounding service supplied to alternating current systems. NEC section 250.92 addresses bonding of equipment containing service conductors. NEC section 250.96 covers bonding other enclosures. NEC section 310.16 provides ampacity tables for conductors. NEC table 250.122 provides minimum equipment grounding conductor sizes for grounding raceway and equipment. Let's consider a scenario. Suppose a 200 amp service is installed in a building. According to NEC table 250.122, the minimum size of the equipment grounding conductor for a 200 amp service is number 6 AWG copper or number 4 AWG aluminum. The bonding jumper between the meter base and the service panel should also be at least this size. The bonding jumper should be connected to the meter base using a listed connector. The bonding jumper should be connected to the service panel using a lug that is listed for grounding purposes. All connections should be made tightly and securely. Now, let's discuss common mistakes. Firstly, improper sizing of grounding conductors. The grounding conductor must be sized according to the NEC to provide a low impedance path for fault current. Secondly, loose or corroded connections. Loose or corroded connections can increase the impedance of the grounding path, reducing its effectiveness. Thirdly, failure to bond metallic enclosures. All metallic enclosures, such as meter bases, service panels, and junction boxes, must be properly bonded to ensure a continuous grounding path. Fourthly, using improper grounding methods. The NEC specifies the proper methods for grounding electrical systems. It is important to follow these methods to ensure a safe and effective grounding system. Fifthly, neglecting regular inspections. The electrical system should be inspected regularly to ensure that the grounding and bonding system is in good condition. Let's dive into different types of grounding electrodes. Firstly, metal underground water pipe. This is one of the most common types of grounding electrodes. The metal water pipe must be in direct contact with the earth for at least 10 feet to qualify as a grounding electrode. Secondly, concrete encased electrode. This type of electrode consists of at least 20 feet of bare copper conductor encased in concrete. The concrete must be in direct contact with the earth. Thirdly, ground ring. A ground ring is a bare copper conductor that is buried in the earth in a ring around the building. The ground ring must be at least 20 feet long. Fourthly, rod and pipe electrodes. These electrodes are typically made of copper or steel and are driven into the earth. Rod and pipe electrodes must be at least 8 feet long. Fifthly, other listed electrodes. The NEC allows the use of other types of listed grounding electrodes. It's also worth noting the concept of grounding electrode system. The NEC requires that all available grounding electrodes be bonded together to form a grounding electrode system. This helps to reduce the impedance of the grounding path and improve the overall effectiveness of the grounding system. Now let's consider the impact of different soil conditions on grounding effectiveness. Soil resistivity is a measure of how well the soil conducts electricity. Low soil resistivity is desirable for effective grounding. Soil resistivity can vary depending on the type of soil, moisture content, and temperature. Sandy soil typically has a higher resistivity than clay soil. Dry soil has a higher resistivity than wet soil. Frozen soil has a very high resistivity. If the soil resistivity is high, it may be necessary to install multiple grounding electrodes or use ground-enhancing materials to improve the effectiveness of the grounding system. Ground-enhancing materials are substances that are designed to reduce the soil resistivity around the grounding electrode. These materials can help to improve the performance of the grounding system, especially in areas with poor soil conditions. Some examples of ground-enhancing materials include bentonite clay, conductive concrete, and chemical ground rods. It is important to select a ground-enhancing material that is compatible with the soil conditions in the grounding electrode. It is also important to follow the manufacturer's instructions when installing ground-enhancing materials. The location of the grounding electrode is also important. The grounding electrode should be located as close as possible to the service entrance. This helps to minimize the length of the grounding conductor and reduce the impedance of the grounding path. The grounding electrode should also be located in an area that is not subject to excessive moisture or freezing. Excessive moisture can corrode the grounding electrode, while freezing can increase the soil resistivity. It is also important to protect the grounding electrode from physical damage. The grounding electrode should be located in an area where it is not likely to be hit by vehicles or other equipment. If the grounding electrode is located in an area where it is subject to physical damage, it should be protected by a fence or other barrier. Let's talk about troubleshooting grounding problems. If you suspect that there is a problem with the grounding system, there are several things you can do to troubleshoot the problem. Firstly, visual inspection. Visually inspect the grounding conductors, bonding jumpers, and connections for any signs of damage or corrosion. Secondly, continuity testing. Use a multimeter to test the continuity of the grounding conductors and bonding jumpers. There should be a low resistance path between all grounded parts of the electrical system. Thirdly, ground resistance testing. Use a ground resistance tester to measure the resistance of the grounding electrode. The resistance should be within acceptable limits. Fourthly, voltage testing. Use a voltmeter to measure the voltage between grounded parts of the electrical system and a known good ground. There should be little to no voltage difference between these points. If you find any problems with the grounding system, it is important to correct them immediately. Contact a qualified electrician to perform the necessary repairs. Neglecting grounding problems can lead to serious safety hazards and potential code violations. Also, consider the role of surge protective devices or SPD in conjunction with proper grounding. SPD are designed to protect electrical equipment from voltage surges caused by lightning strikes, power line disturbances, and other transient events. SPD work by diverting surge current to ground, thereby protecting the connected equipment from overvoltage damage. The effectiveness of an SPD depends on a properly grounded electrical system. A low impedance grounding path is essential for the SPD to quickly and effectively divert surge current to ground. If the grounding system is inadequate, the SPD may not be able to protect the equipment from damage. The NEC requires that SPD be installed in accordance with the manufacturer's instructions. It is important to follow these instructions to ensure that the SPD is properly installed and will provide adequate protection. SPD should be installed at the service entrance, as well as at other locations throughout the electrical system to protect sensitive electronic equipment. SPD are available in a variety of types and sizes to meet different needs. It is important to select an SPD that is appropriate for the application. Factors to consider when selecting an SPD include the voltage rating, the surge current capacity, and the protection level. The voltage rating of the SPD should be equal to or greater than the nominal voltage of the electrical system. The surge current capacity of the SPD should be sufficient to handle the expected surge currents. The protection level of the SPD should be low enough to protect the connected equipment from damage. Now let's discuss the importance of documentation and labeling. It is important to document the grounding system, including the location of grounding electrodes, the size of grounding conductors, and the types of grounding connections. This documentation can be helpful for future maintenance and troubleshooting. The NEC requires that certain parts of the grounding system be labeled. For example, the grounding electrode conductor must be labeled to identify its purpose. The labeling should be clear and legible, and it should be permanently attached to the equipment. Proper documentation and labeling can help to ensure that the grounding system is properly maintained and that it is safe and effective. In summary, understanding the principles of grounding and bonding is essential for electrical safety. A properly grounded and bonded electrical system helps to protect equipment, reduce the risk of electric shock, and minimize the likelihood of fire. Always consult with a qualified electrician and follow the applicable electrical codes when working with electrical systems.